Okay, and so last time we finished up our discussion of Fourier series for this class. And so in the second part of the last lecture, we began introducing what's called Laplace's equation. And so we're going to be studying this equation in both 2 and 3 dimensions. And so remember, what does Laplace's equation say? Well, it says that if you have a function u of either 2 or 3 variables, then if you take the Laplacian of u, then that is equal to 0. Right, and so remember the Laplacian, what is the Laplacian? Well, you take the second derivative with respect to each variable separately, and then you add those all together, right? So for example, in 2 dimensions, the Laplacian is uxx plus uyy is equal to Laplace u in 2 dimensions. And in 3 dimensions, well, let's say the function u is a function of x, y, and z. Well, then you have uxx plus uyy plus uzz is equal to Laplacian u. Right. And so, right, so we're going to study this equation in detail over the next several lectures. And so, right, so we'll be looking at both the homogeneous version of this equation where the Laplacian of u is equal to 0, and the non-homogeneous version of the equation where the Laplacian of u is equal to some given function f. And so in the non-homogeneous case, this is often called the Poisson equation, or you can refer to it as non-homogeneous Laplace's equation. Right, and so we saw last time as well that typically solutions to the Laplace equation are called harmonic functions. Right, and so what we're going to be doing now is studying harmonic functions in detail, right? So whenever I say harmonic function, what we mean is solution to Laplace's equation, right? Or the Laplacian of u is equal to 0. And so we saw at the end of the last lecture a few examples of where this equation arises. So the Laplace equation is one of the most fundamental partial differential equations in math. And it arises in a variety of different contexts. And so whether you're interested in like pure math or financial math or engineering or physics, it really helps to know the basics of how to analyze and solve the Laplace's equation because it shows up in a wide range of topics as we saw. And so I just wanted to mention briefly in a little bit more in detail. I mean, I mentioned this verbally in the last lecture, but I don't think I wrote it down. So why aren't we looking at Laplace's equation in 1 dimension? Well, remember the Laplacian just means you take second derivative with respect to each variable separately and then add those quantities together, right? But if I only have 1 variable, then the Laplacian just reduces to second derivative with respect to that variable, right? So for example, let's say I'm looking at a function u of x, right? And I'm taking the second derivative with respect to x. Well, then Laplace's equation just says that the second derivative of my function is equal to 0. But you can just take 2 antiderivatives, right? So this says that the first derivative has to be some constant, say b, or sorry, say a. And then if I take 1 more antiderivative, we can conclude that the function u has to be equal to, say, a times x plus some other constant, right? But this means that my function u, which is a solution to the Laplace equation in 1 dimension, is just a linear polynomial. And these are the only solutions, right? And so it turns out that in 1 dimension, the Laplace's equation is not very interesting because we just found all the solutions in 10 seconds. And so basically all the theory is done, right? Laplace's equation in 1 dimension are just linear polynomials. However, we'll see very quickly that as soon as you pass to 2 or 3 dimensions, it becomes much more complicated and interesting. And so the theory is much deeper in 2 and 3 dimensions. Okay, and so what we're going to be doing, similar to what we did when we first studied the diffusion equation, is begin by looking at some properties and some symmetries of solutions to the Laplace equation. And so that's what we'll basically be doing for the rest of the lecture today. And then in subsequent lectures, say the next 2 or 3 lectures, we'll talk about different methods for solving this equation in different domains. Okay, and so the first thing we're going to talk about should be familiar if you think back to what we saw in the case of the diffusion equation. So remember, if you have a solution to the diffusion equation on a finite domain, it always had to satisfy this maximum principle, which says that if you look at the largest values of the solution for the diffusion equation, these have to occur on a certain region in the boundary of the domain. Well, as we saw in the last lecture, there is a pretty deep connection between Laplace's equation and the diffusion equation or the heat equation. In particular, the Laplace's equation is somehow like an equilibrium or a steady state version of the diffusion equation after time has evolved to infinity, right? So the system has approached some equilibrium, and so there's no more change with respect to time. And so the partial derivative with respect to t terms vanishes, and then you're just left with Laplacian of u is equal to 0, right? So you can derive the Laplace's equation from the diffusion equation. And so you should expect that some version of the maximum principle could hold, which is the case, right? And so in fact, we actually have what we call the strong maximum principle for harmonic functions, right? And this is going to, again, look very similar. So what is the maximum principle for Laplace's equation? Well, let's suppose we have a finite domain D, right? Say some bounded domain. And let's assume it's in one piece, meaning more precisely, it's a connected domain. Right, so connected means it's one piece. Let's suppose that we have, actually, let me just, right, so what do I mean by a domain? I mean like some region in 2 or 3 dimensions. Like say this is my domain D with some open interior. And then this line, or sorry, this boundary region that encloses the domain will denote, well, since it's the boundary, we'll denote it following the Book's notation as boundary of D, right? So the boundary is the region outside the region surrounding the domain, right? That separates it from the rest of the plane in this example, or separates it from the rest of space in 3 dimensions. Of course, you can write down a more precise definition of what the boundary is mathematically, but I don't want to distract too much from just the statement of the theorem here. You can of course look that up in the book. Right, and so we're going to assume that our function u is harmonic in this domain. Right? So suppose u is harmonic in D, meaning it's a solution to Laplacian of u is equal to 0. Right? So inside this region, Laplacian of u is equal to 0. Right, and so when I say it's harmonic in D, we mean that at any point inside this region, so it may not necessarily be harmonic on the boundary. So this is not required. Right, so all we require is that if you pick some point inside this region, then it's harmonic at that point, right? However, in order for this theorem to work, we do need a technical assumption about the behavior on the boundary as well. And it's enough to assume that the function u is continuous up to the boundary. Right? So suppose u is harmonic in the domain D and continuous up to the boundary. Right, and so what do I mean by continuous up to the boundary? That just means that if I consider, like say, a sequence of points converging to the boundary, and I look at the values of my solution at those points, well, then this should continuously converge to the value at the limiting point on the boundary, right? So it's like it's just the standard definition of continuity, but I want to allow to change my input in the domain, and it should vary continuously up to and including the boundary, right? The values of my function should vary continuously. Right, so these are the assumptions, and so what is the conclusion? The conclusion is that both the maximum and minimum values of the solution u, or of the harmonic function u, are attained in the boundary and nowhere else. Except in one case, if u happens to be a constant function, then this will fail, unless u is constant. Right. And so notice that this is indeed the strong maximum principle as we described for the diffusion equation. So this doesn't just say that the largest and smallest values occur on the boundary. It also says that they can't occur anywhere inside the domain, right? They have to only be on the boundary, right? So if you have any point inside the domain, right, say this point here, well, here U is strictly between the maximum and minimum of U. Right, so it can only equal its minimum value, its smallest value, or its largest value on the boundary and nowhere else. So this is what the theorem says. Right, and so there's one additional point here which we didn't really discuss when we talked about the diffusion equation, which I want to mention briefly. So why do we need the domain to be connected, right? What is the reason that we need the domain to be in one piece? Well, we can come up with actually a pretty simple example to show that this hypothesis is necessary. So let me just discuss that briefly. Right, so why do we need this hypothesis? Well, let me define a domain D that is not connected, meaning it's in two or more pieces, right? So maybe let me call this the first piece, which I'll call D1, and let me call this region here D2. And let me define my domain D to consist of both of these regions. Right, so D is both combined. Right, well, I can define a function now that's harmonic and not constant on this domain for which the maximum function fails. And so, well, when you first like are given like this type of problem, you may think, well, how am I going to just come up with a function for which this fails? It turns out for this example, it's actually relatively easy to do because remember, well, harmonic functions satisfy Laplacian is equal to 0. But if U is just equal to some constant number, then of course, any derivatives are 0. So any constant function is harmonic. And so let me define, let's say U is identically equal to 1 in D1, and U is identically equal to 2 in D2, right? So this means that if we only consider the function D1 or the domain D1, then our function U is equal to 1 at every point here. And if we only consider D2, then our function U is equal to 2 at every point here. But we're considering the domain, which is the combination of both of these. So U is no longer a constant function because it takes two different values depending on which domain you're in. Well, as we just mentioned, Laplacian of U is equal to 0, but the strong maximum principle fails. Right, because this function U is not constant on the domain D, since you can alternate between 1 and 2 depending on which part of D you're in, but the Laplacian is 0, so it's harmonic. And the maximum principle is failing because, well, what's the largest value? The maximum value is 2. The max value is attained everywhere inside D2, not just on the boundary, right? On the other hand, the minimum value is 1, and the minimum value is attained everywhere in D1, not just on the boundary, right? And so the strong maximum principle fails. Right, so just very briefly, what do I mean by the boundary of D? The boundary of D is mathematically defined to be the both of the boundaries of D1 and D2 respectively combined, or the union of the boundaries. Right, so it's boundary D1 union with boundary D2. And so that means that it's this region and this region combined. The two blue curves are the full boundary of the domain. Okay, and so this example is kind of like the technical reason why we need this connectedness hypothesis. As long as you understand this example that we just went through, I wouldn't worry otherwise too much about the connectedness hypothesis. But it's important to just be aware of this restriction. Okay, and so we're going to prove the maximum principle for harmonic functions, and it's going to turn out that the proof that we use will be a little bit easier than the proof for the diffusion equation. However, we're going to wait until later in our discussion because in a few lectures, we're going to have a new tool which will make it a lot easier to prove this. And so I'm going to defer the proof of the maximum principle for another few lectures. Right, so it is possible to just use an argument very similar to what we saw for the diffusion equation, which is written out in the textbook in the corresponding chapter 6.1, which you can read if you're interested, but we'll have a slightly easier proof in a few lectures, which is, I think, a little bit more insightful and also saves a little bit of time as well. So it's like one of these like very good proofs, which is shorter and also tells you something new or is intuitive. Right. Okay. And so, well, if you remember, one of the major applications of the maximum principle for the diffusion equation was for proving uniqueness for certain boundary value problems. And so, well, you can similarly use the maximum principle to prove uniqueness for Laplace's equation. Right. So let's suppose we have a domain D as before with the boundary, right? And so suppose, or let's consider the following boundary value problem. Right, so let's suppose that the Laplacian of my function u is equal to some function f inside the region in the domain D. And let's suppose that I have a certain boundary condition, say u is equal to h on the boundary of D. Right, so this is the Dirichlet problem, the Dirichlet boundary conditions. So f could be 0, or f could just be an arbitrary function that's given to you as long as f doesn't depend on u, right? And similarly for h. So f and h are given functions. Right, so h is a function on the boundary, and f is just a function in the domain D, right? And so the domain D is also satisfies all the hypotheses from the theorem above, right? It's connected and so on, right? And so the theorem is that there is at most one solution, which is the uniqueness theorem. Right, so we still don't know if there exists any solutions. There could be no solutions. But what this theorem at least says is that if there's a solution, there's only one. And so remember, these uniqueness results are very important for application because we want to make sure that this is kind of accurately describing some real world system. Right, but in the real world, we expect in most scenarios for like basic principles of determinism to hold, right? At least for short periods of time. And so in order for this to really be deterministic, you need to, I mean, the boundary conditions should uniquely define what the function looks like, right? So this is, we discussed this a little bit for uniqueness problem for the diffusion equation, right? And so how do we prove this? Well, the proof should be very familiar from all these arguments we did for uniqueness of the solutions to the diffusion equation in finite domains. So in particular, let's suppose that we have two solutions, say u and v both solve the boundary value problem. As we've done a million times by now, we're going to define the difference of these two functions, right? Well, since the Laplace's equation, or in this case, the non-homogeneous version of it, which is Poisson equation, well, since this operator on the left is linear, we can calculate the Laplacian of w. This is the Laplacian of u minus v. It's linear, so this is Laplacian of u minus Laplacian of v. Both of these solve the boundary value problem, so this is f minus f. Of course, the function minus itself is always equal to 0. So w is harmonic, right? Also note that, well, what happens on the boundary, right? So on the boundary, well, W is equal to U minus V. At each boundary point, U and V are both equal to H because they solve the BVP. So this is equal to H minus H, which is 0. And so therefore, W is a harmonic function with W identically equal to 0 on the boundary of D. And so we're just going to apply the maximum principle. Right? And so it's harmonic. So that means that by the maximum principle, the largest and smallest values have to occur on the boundary, right? But it's equal to 0 at every single point on the boundary, right? So the maximum principle tells us that the maximum of W in the domain D is 0, since W is equal to 0 at every point on the boundary. And also that the minimum value of W is equal to 0 at all points, right? So that means that, well, W is always bigger than or equal to the minimum and always less than or equal to the maximum for all points. And so therefore W is identically 0, right? But since W is equal to 0, that means that at each point, we have 0 by definition of W, 0 is equal to U minus V. And so this implies that U equals V for each point. Right, and so that's the proof. Again, very similar to what we saw in the case of the diffusion equation. Again, the key point was we want to show there's only one solution. So let's assume we have two and show that they're the same function, right? How do you show that they're the same function? Well, one way to do that is to show that their difference is equal to 0, right? And so we let W equal their difference. And since the equation is linear, that's a harmonic function. And then we apply the maximum principle. Okay. Right, so this is good because it tells us that when we look at boundary value problems later on, which we will do, that when we talk about the solution, we really mean it's the only solution, right? We have uniqueness. Okay, and so the next thing I want to talk about are certain symmetries related to the equation. And so we're going to look at invariance of the Laplacian under certain symmetries. Right. And so up until now, the arguments that we've been given will apply equally in both 2 and 3 dimensions. Remember, everything here is valid in either 2 or 3 dimensions, right? The maximum principle and the uniqueness result. Well, when you talk about different symmetries that the Laplacian, that are related to the Laplacian, well, here we have to a little bit more carefully take into account which dimension we're in, because different dimensions will have different kinds of symmetries, right? Because if you move to higher dimensions, there's more space, right? So there's more symmetries. Right, and so what we're going to begin with is the 2-dimensional case, right? And so let's begin by looking at the 2-dimensional. Right, so in this case, let's say we use x and y coordinates as is normal. So the Laplacian is given by second derivative with respect to x plus second derivative with respect to y. And so we're going to, again, look at different like actions on the plane, which will leave the action of the Laplacian invariant. And so more precisely, we're going to prove in part the following theorem. So the Laplacian in 2 dimensions for now is invariant under translations of space and rotations of the plane, right? And so what do I mean more precisely? Suppose, let's say x bar, y bar is obtained by rotating or translating x comma y. Right, so here x comma y are my usual coordinates for the xy plane. Let's say I define new coordinates by rotating those or translating them. Then if I take second derivative with respect to x plus second derivative with respect to y, well, this is the Laplacian in the usual coordinates. This is equal to second derivative with respect to the new x bar plus second derivative with respect to the new y bar of my function. Right, so this is Laplacian in x bar, y bar coordinates. Right, so again, this means if I change, so think back to the beginning of the class when we talked a little bit about the coordinate method. If I use the coordinate method and define new coordinates by rotating my original coordinates in the plane, then that doesn't change the value of the Laplacian for any function, right? So this quantity here is always equal to this quantity here. Right, so for example, maybe this is my, say this is my point xy, or these are my, let me do this slightly differently. Right, say this is my x-axis, this is my y-axis, and maybe I rotate by like a certain angle, like say I rotate by some angle theta, and so this is x bar, and then maybe y bar goes over here. Right, so x moves to x bar, y moves to y bar. If I use these new coordinates to define my Laplacian, it doesn't change what the Laplacian does to the function. That's the point. Right, and so this may seem like kind of a technical result, but it's important for applications, in particular in physics, right? Because there are a variety of phenomenon in physics which will be described using the Laplacian. And so in physics, you don't want necessarily any distinguished set of coordinates or any distinguished reference point, right? Because for example, if you consider like the motion of a moving object, or maybe like an electromagnetic wave moving through space, the behavior of that thing is independent of which coordinates you fix to analyze it, right? And so these equations that we're looking at should hopefully be invariant under basic symmetries like this of space, or else there could be some problems in applying them, right? And so this is one reason why this result could be important. Mathematically, it's also important because sometimes you can take advantage of these symmetries to simplify a lot of calculations, right? Maybe at one coordinate system, it's harder to understand what the Laplacian of your function looks like, but you could change your coordinates by rotating, and then maybe it'll make your calculation easier without changing the value of what you're trying to find. Right? Okay, and so what I'll do is I'm just going to prove this in the case of rotations. It's actually easier to prove it in the case of translations. Maybe you can model what I do for the case of rotations and see how to prove it in that case as well. Okay, and so in order for this to work, we do have to use a little bit, sorry, in order to prove this, we do have to use a little bit of linear algebra. So it could be helpful to, if you get stuck here, to pause for a little bit and review some basic properties from linear algebra, which we're using here. Again, you can take advantage of the fact that this is online. You don't have to watch this all from front to back. You can pause it and look up some things if you haven't thought about these methods in a while. Right, and so in particular, well, we're going to recall that, well, actually, let's suppose as above that x bar, y bar is given as rotation of x comma y by an angle theta, say. Well, we can describe this using the action of a matrix. So in particular, we have x bar, y bar is equal to the matrix cosine theta, sine theta, minus sine theta, cosine theta, applied to my original coordinates. Right, so this is a rotation matrix. Right, and so this means that if I start with my original coordinates x comma y, I apply this rotation matrix, it gives me my new coordinates. And geometrically, what happens is I just take the point x comma y and I rotate it by theta, right? By the angle theta. And so what does this say in terms of if I write out the definition of the action of this matrix? Well, we end up with formulas for x bar and y bar in terms of x and y. And in particular, x bar is equal to x cosine theta plus y sine theta. And y bar is given by minus x sine theta plus y cosine theta. Right, so all I've done here is write out what does it mean to apply this matrix to this vector. This is what you'll get if you do that. And so now what we're going to do at this point, well, we've described the rotation analytically, and now we just have to calculate, right? And so what we're going to do is calculate the second derivative with respect to x bar and the second derivative with respect to y bar, and use the chain rule and show that this is the same thing as what you get over here. Right, and so in particular, let's use the chain rule to calculate. And so let's begin by looking at, well, what is the first derivative? I mean, in order to understand second derivatives, we first have to understand first derivatives. So let's first look at derivative with respect to x and try to write this in terms of x bar and y bar. Well, if I use the chain rule, this is equal to derivative with respect to x bar times dx bar dx plus derivative of u with respect to y bar times dy bar dx. Right, so this is the chain rule. And so therefore, we get ux is equal to, well, what is dx bar with respect to x? Well, this is x bar is equal to x times cosine theta plus y times sine theta. The only thing that depends on x here is the first term. If I take derivative of this term with respect to x, I just get cosine theta. So this is going to equal cosine theta times ux bar. Similarly, the derivative of y bar with respect to x is equal to negative sine theta. Right, so I'm going to get plus minus sine theta uy bar. Right. And well, similarly, we can calculate the first derivative with respect to y. Right, so derivative with respect to y is given by ux bar times dx bar with respect to dy plus uy bar times dy bar dy. Right, so this is again the chain rule. And so this tells me that derivative with respect to y is equal to, well, now what is dx bar dy? That's sine theta. So sine theta ux bar plus what is dy bar dy? That's cosine theta uy bar. Right? And so now we know what the first derivatives with respect to x and y are in terms of x bar and y bar. And in particular, we have the following formulas. So since this is true for any function u, right? So therefore, well, we know that what is the derivative with respect to x? This looks like cosine theta times derivative with respect to x bar minus sine theta times derivative with respect to y bar. And derivative with respect to y is equal to, well, the same thing as sine theta times derivative with respect to x bar plus cosine theta times derivative with respect to y bar. Right, and so just using the chain rule, we've found a way to write our standard differential operators in terms of the new coordinates. Right, so this is very, very similar to the types of calculations we did when we were using the coordinate method to study the wave equation, for example. It's the same idea here. Okay, and now let's continue calculating. We don't just want first derivatives, we want second derivatives. So now let's calculate uxx using this. Right. Well, remember, this is the same thing as the x derivative of just ux, right? And well, we have a formula for ux. So this is cosine theta times ux bar minus sine theta times uy bar. and we're taking the x derivative of all of that. So now what I'm going to do is use the fact that differentiating is a linear operation. So this is the same thing as actually, we will use the linearity. Let me not use the linearity yet. Let me write this as derivative with respect to x of this operator applied to what I have here. Right. And so from up here, we know how to write this operator in terms of the new coordinates, right? Sorry, this should be a y, that may not be clear. Right, and so let me now plug in this definition for d dx. And so I end up with, well, I have cosine theta times d dx bar of everything in brackets. And then I have the second term corresponding to d dy bar, the second term. So I have to subtract sine theta d dy bar times the same quantity in brackets. Right. And so now I'm just going to distribute and evaluate everything. And so we end up with uxx is equal to, well, I have cosine theta squared. Now I'm going to use linearity of the differential operators. So I get cosine theta squared, u x bar minus cosine theta sine theta, u x bar y bar. Remember, the order in which I take partial derivatives doesn't matter. And then I have two more terms. So I get minus sine theta cosine theta, ux bar y bar. And then finally, I get plus sine squared theta, uy bar y bar. Right. Right. And so all that work tells us what the second derivative with respect to x looks like. So similarly, we can calculate second derivative with respect to y. Right, so we have uyy is equal to, well, we already calculated uy, right? And so this is just the derivative of uy with respect to y again. Let's plug in the formula we had for uy, which was up here. Right, so I'm going to plug in sine theta ux bar plus cosine theta uy bar. Right, so this is d dy of sine theta ux bar plus cosine theta uy bar. And now I'm going to replace derivative with respect to y using our formula by derivative with respect to the new coordinates in this way. Right, so this now simplifies to sorry, what was the, right? So sine theta d dx bar plus cosine theta d dy bar, all applied, right? So I've replaced d dy with this quantity here, and then all applied to what we had in brackets. So sine theta ux bar plus cosine theta uy bar. And so now I'm going to evaluate everything distributing through using the linearity as before. And so this ends up being, maybe I'll move a little faster on the calculations, but of course, if I write something down that confuses you, you can pause and just check the calculations yourself. So this ends up being, well, I have sine squared theta ux bar x bar plus sine theta cosine theta ux bar y bar. So that comes from distributing this term using the linearity. And then I'm going to distribute the second term. So I end up now with plus cosine theta sine theta ux bar y bar. And then finally plus cosine squared theta uy bar y bar. Right. And so what happens now if I add these two quantities? right? So I calculated uxx in terms of x bar and y bar here, and I calculated uyy in terms of x bar and y bar here. And so now let's add these together. Well, notice if I add these together, let's collect the like terms. So in front of x bar, I have cosine squared plus sine squared, right? And in front of y bar, I have sine squared plus cosine squared. Okay. Actually, let me use different colors to not confuse. Right. Well, remember, cosine squared plus sine squared is equal to 1. So those terms will simplify a little bit, right? But for the remaining terms, I have the same things with opposite signs, right? So when I add the remaining terms together, I have here cosine theta sine theta minus 2 cosine theta sine theta times ux bar y bar. Here I have positive 2 times sine theta cosine theta ux bar y bar. So when I add those together, they're going to cancel. And so if we do this algebra, we end up with adding these two quantities together. This is cosine squared theta plus sine squared theta ux bar x bar plus the same thing in front of uy bar y bar, and then plus 0, right? Because other terms cancel. But again, as I just said, remember cosine squared plus sine squared of a fixed angle theta is always equal to 1. So this says that uxx plus uyy is equal to ux bar x bar plus uy bar y bar, right? And so this proves, as claimed, that the Laplacian is invariant under this rotation operation, right? So if I change my coordinates xy to x bar y bar using a rotation, the action of the Laplacian doesn't change on the function. You get the same output when you apply Laplacian in either coordinates. Okay, and the proof for translations is similar and actually a little bit easier. So I'm gonna omit that. Okay, so if you think back to multivariable calculus, there was a specific coordinate system which was very useful for analyzing things that involve lots of rotations. And so in particular, this was the polar coordinate system. Right, and so remember, if this is the standard x and y axis, maybe this is a point x comma y. How do we define polar coordinates? Well, polar coordinates are given by a choice of length r, which is given by the length of your vector from the origin, or the distance between your point and the origin, and then an angle theta, which is chosen to be the angle that your point, or that the vector that ends at your point makes with the x-axis, right? And so these are polar coordinates. And so since the Laplacian is invariant under rotations, and since polar coordinates involve like understanding like a rotation from the x-axis to your point, you would think that maybe if you use polar coordinates, the Laplacian may have some nice symmetries or look nice in terms of these coordinates. And so that generally turns out to be the case in both 2 dimensions and higher dimensions. And so what I want to do is just briefly discuss what happens if you try to describe the Laplacian in polar coordinates, right? So what happens if I do a change of coordinates to r theta and try to write my Laplacian in terms of these coordinates? Well, remember, how do these coordinates relate back to the others? Well, r is the length of this vector, so it's the square root of x squared plus y squared. Right, and theta is given by right. So this is my x value. This is my y value. So if you look at the tangent of theta, this is given by y over x, right? So theta is given by the inverse tangent, or the arctangent of y over x. On the other hand, if you go from if you know the polar coordinates and you want to determine x and y in terms of r and theta, the formulas are a little bit simpler. So x is given by r sine theta, and y is given by r cosine theta, right? And so if you use these new coordinates, again, the question is what happens to the Laplacian? And so let me just write this as a theorem. So in polar coordinates, right? So what I'm going to do is view u as a function of r and theta rather than a function of x and y. The Laplacian of u is given by, well, you have second derivative with respect to r, and then you have plus 1 over r times the first derivative with respect to r, and then you have a term corresponding to theta. You have 1 over r squared times second derivative with respect to theta. Right. And so how do you prove this? Well, the argument is very similar to what we just did to prove the rotation invariance. You use this coordinate change in the chain rule, and you try to calculate what uxx and uyy look like in terms of these new coordinates. And then you simplify everything and you get this formula. It is a pretty lengthy calculation, so I'm going to omit it from the lecture for two reasons. The first reason is we just saw a very similar calculation for proving the rotation invariance a few minutes ago. And also this calculation is written out in detail in the textbook, so you can read it yourself. So a third reason is actually it's probably a good exercise at least once to try to do this. It's a good way to practice using the chain rule and to practice the coordinate method for the Laplacian. Right. Okay. Excuse me. But what we will do instead of proving this is look at an interesting application of this result. So notice that if I look at this formula, so let's say we look at the term involving the angle theta, right? Well, let's suppose that we have a function that does not change with respect to theta, right? So suppose our function u is independent of theta, right? So analytically, that means that u is some function of r, right? So there's no dependence on theta, and in particular, u is a one variable function, right? Or it can be viewed as a one variable function of just the radius parameter r. Well, geometrically, if we go back here, this means that the value of the function doesn't depend on theta. It only depends on the radius, right? So let's try to look at geometrically what this means. Right, let's say I pick a point with a particular radius r. Well, I can look at the whole circle of radius r centered at the origin, right? And so u has the same value at all points on the circle of radius r. Right. Of course, if you change the radius r, u is some function of that parameter r, so the values of u could change on different circles. But if you fix one such circle, it has the same value at every point, right? And so this means that the function u is invariant under rotations, right? Because if I rotate, I'm not changing the value of r, I'm staying on the circle if I rotate, and so the value of the function stays the same, right? And so analytically, the way to say that it's rotation invariant is that it's only a function of r in polar coordinates. It doesn't depend on theta, right? But in this case, well, this term is going to vanish from the Laplacian. And so we can calculate and see that the function, we can actually solve the equation directly in this case. Right, so in this case, if I take the second derivative with respect to theta of u, this is the second derivative with respect to theta of just a function of r. Since it doesn't depend on theta at all, this is just 0 because it's constant with respect to theta. It only depends on r. And so this tells me that the Laplacian of u is given by second derivative with respect to r plus 1 over r times the first derivative right? And so let's solve the Laplace equation for this particular function, right? So suppose u is harmonic, meaning the Laplacian of u is equal to 0, right? Well, what is, if I use polar coordinates, sorry, this says that if I take, well, now u is just a function of r, so let me just write this as u prime prime of r plus 1 over r times u prime of r is equal to 0. Well, let's suppose r is not equal to 0, because if r is equal to 0, we're just at the origin, and it doesn't. We can let's just exclude that point for now. Well, in this case, I mean, this formula is really only valid when r is not equal to 0 anyway, right? Because otherwise this would be infinite, right? So we can assume r is not equal to 0, otherwise the formula doesn't make sense. Let's multiply by r, right? So this is equivalent to r times u prime prime of r plus u prime of r is equal to 0. But you can recognize the left-hand side as the derivative with respect to r of u prime. Right? This is just the product rule. Oh, sorry, not of u prime, of r times u prime, excuse me. Right? So you can recognize the left-hand side as derivative with respect to r of r times u prime of r. And this is just the product rule, right? Which you can check. Well, that means that the function in parentheses is constant with respect to r, right? So this says that r times u prime of r is some constant c1, right? So u prime of r is equal to c1 over r, right? R is always positive, right? And so this tells me that u of r is equal to, well, let's take the antiderivative. If we take the antiderivative, we get c1 times natural log of r. To avoid, right, let me write this as natural log of r plus c2, right? Taking the antiderivative, right? And so that tells us that this is a harmonic function, right? This solves the Laplace's equation on the plane. Well, remember that we know how to write r in terms of the original coordinates. R is square root of x squared plus y squared. And so therefore, if we define u of xy is c1 times natural log of square root x squared plus y squared plus c2, this is harmonic. Right? And so this turns out to be a very important type of harmonic function, which is analogous to the source function for the diffusion equation, which you can use to construct other solutions. So we'll see a little bit more about this later on. Okay, so this was all in 2 dimensions. I also want to discuss what happens in 3 dimensions. Right, so now we're going to be looking at the Laplacian. Let's view u as a function of x, y, and z. Right, so Laplacian of u is given by u xx plus u yy plus u zz. Right, and so there's the corresponding invariance theorem. Right. So we're going to define rigid motion in space. Right, so since now we're in 3 variables, we're looking at the Laplacian equation in 3D or in space. So a rigid motion in space is a combination of a translation and a rotation. Right, so for example, you can translate your coordinates or rotate your coordinates. And so the theorem says that in the same way as in the two-dimensional case, the Laplacian is invariant with respect to rigid motions. Right, so in the following sense, so if, say, x bar, y bar, and z bar is the image of the standard coordinates under a rigid motion, meaning a translation or rotation or some combination of the two, then we have a similar formula. So then ux bar x bar plus u y bar plus u z bar, which is the Laplacian in the new coordinates, is equal to the standard Laplacian. Right. And so the proof of this theorem is very similar to the argument given in 2 dimensions. So you have to use the chain rule to calculate what these coordinates, the action of the derivatives with respect to x, y, and z look like in terms of derivatives with respect to x bar, y bar, and z bar. Since we're in 3 dimensions, the geometry is a little bit more complicated. And in particular, you have to use a little bit, I mean, the linear algebra you have to use, the calculations are a little bit longer and more involved. It's written out in detail in the textbook. I think maybe some important details are omitted from the discussion in the book. But what I can do is maybe quickly type up a proof of this result and attach it to our, I'll upload it to our website. So if you're interested in seeing a proof of this result, for example, in the case of rotations, I'll have that typed up and posted on the website. Otherwise, I'm going to omit it from the lecture because it really is just a very long calculation, which is already similar to what we did in the 2-dimensional case. So I think it would be better to leave it as like as an extra note if you happen to be interested in how the proof works. Instead, what we'll do is move on and do something similar to what we talked about in the 2-dimensional case and think about what this means for certain coordinate systems in 3D. And in particular, well, there's a natural generalization of polar coordinates to 3 dimensions, which also take into account which are also very useful if your objects behave well with respect to different rotations. For example, if you're looking at like the integral on a sphere or something like that. And so remember, these are typically known as spherical coordinates. Right, so we want to talk briefly about the Laplacian and spherical coordinates. Right, and so let's suppose we use the standard coordinate system in 3 dimensions. So let's say this is the x-axis, this is the y-axis, and this is the z-axis. And let's fix a particular point, say x, y, z in the 3D coordinate system. Well, spherical coordinates are usually described as some parameter r, which is the length of this vector, and then 2 angles theta and phi. Right, so r is going to be the length of this vector, so it's the square root of x squared plus y squared plus z squared, right? And then, well, how do you define phi? Well, let's drop down this vector to the xy plane and look at the kind of like the shadow or the projection on the xy plane. This projection makes a certain angle phi with the x-axis. All right, so we'll call that phi. And then also, well, if we go back to our original vector x, y, z, let me draw it in vector with a vector notation. If we go back to our original vector, this also makes an angle theta with the z-axis, right? And so these are the definitions of these coordinates, right? So it turns out that as long as you specify a radius r, you specify this angle phi in the xy plane, and then you specify the angle it makes with the z-axis, you can describe every point in space in this way. right? So this is indeed a full coordinate system for 3D, which is again useful if you're dealing with problems which have certain symmetries related to rotations. Like for example, if you're looking at the triple integral of a function on a sphere, the sphere is very easily described using spherical coordinates, so it may be better to use these rather than the standard Cartesian coordinates of x, y, z. Right, and so what we'll do to finish up the lecture today is look at what happens to the Laplacian in these coordinates. Right, so I just wanted to include two brief comments. The first is, well, how do I relate these coordinates, x, y, and z, to the original coordinates? Well, there's standard formulas which are similar to what we saw in the case of polar coordinates. So right, you can maybe review those in the textbook or look them up. It would be helpful to review them. Another thing I want to point out is that maybe as a warning, so when you see other sources talk about spherical coordinates, usually theta and phi are reversed. Meaning most books will use theta to describe phi here and phi to describe theta here. Like this is the more standard way of talking about notation for spherical coordinates. But our textbook uses this notation. And so I didn't want to contradict the notation in the textbook. So I want to be consistent with the book. And so I'm using this slightly less standard way of describing spherical coordinates. Of course, this is just a matter of notation, right? Mathematically, it's the same thing. It could be confusing if you look at formulas, and that you may mix up the roles of theta and phi. So be very careful when you do that. Right. Okay, and so well, now let's get to the main point. So if you write the Laplacian using spherical coordinates, what does it look like? So the theorem is the following, right? So let's view u as a function of spherical coordinates. Okay, so we're going to use spherical. The theorem is that then the Laplacian of u can be calculated using spherical coordinates in the following way. Well, you take second derivative with respect to r plus 2 over r times first derivative with respect to r. Right, so these are the two quote unquote radial terms which involve the parameter r, which is related to the radius of the sphere that your point lies on. And then we have a variety of terms that correspond to the different angles theta and phi. So the remaining term is 1 over r squared times u theta theta plus cotangent of theta times u theta plus 1 over sine squared of theta times u phi phi. Right. And so this can also similarly be proved using the coordinate method, and in particular using the chain rule to calculate what the different partial derivative operators with respect to x, y, and z look like in terms of r theta and phi. Once again, it's an even longer calculation, which we're going to omit from the lecture, although it's very similar to the types of arguments we've discussed earlier today and we've seen earlier in the class. So you can look this up in the textbook as well. Right. And so to finish the lecture, we're going to do a similar type of analysis to what we did in the two-dimensional case. So let's suppose that I have a solution or a function u that doesn't depend on theta or phi. Right? So suppose u is independent of theta and phi. Right? So u is just some function of r. Right? Well, this means that if I look at u theta is equal to 0 because it doesn't depend on r, and also u phi is equal to 0. And so, of course, if the first derivatives are 0, the second derivatives are also 0. right? So for this special class of functions, which only depend on the radius parameter, this term vanishes and the Laplacian acts very nicely on these functions. It's a lot easier to calculate the action of the Laplacian, right? And so let's do this in detail. So suppose U is radial or rotation invariant in the sense that U equals just a function of R. In particular, it's a one variable function of just the radius. And it's independent of, it doesn't depend on theta and phi, right? So geometrically, this means that let's pick a point x, y, z in space. This point lies on a particular sphere centered at the origin with a particular radius. And the value of U at that point only depends on the radius, right? So at every point on this fixed sphere, U has the same value. Although if you change the sphere with a different radius, maybe U has a different value, right? Well, if I take the Laplacian of U, we're only going to have two terms here, and they're both just one variable derivatives with respect to R. And so we're going to be able to calculate the solution, right? Right. So suppose also that U is harmonic. Right, so Laplacian of U is equal to 0. Well, now let's use this formula. So then we get 0 is equal to Laplacian of U, which is equal to URR plus 2 over R UR. The rest of the terms in the formula for the Laplacian are complicated, but since U doesn't, all those derivatives of U are 0, they just contribute 0 here, right? So I can just eliminate those terms, right? Okay, now this is just an ordinary differential equation in the variable R as before. And so let me rearrange this. Once again, we're assuming R is not 0. So we can multiply through. In this case, since I have a 2 here rather than a 1 like we did in the last case, it helps to multiply by R squared. And so if I multiply by R squared, I get R squared URR plus 2R UR is equal to 0. But now we can recognize this quantity here as the derivative with respect to R of R squared times the first derivative of U with respect to R, right? Once again, using the product rule, right? And so this tells us then, well, if this quantity in parentheses is equal to 0, or sorry, has derivative equal to 0, then the quantity in parentheses has to be a constant, right? So this tells you that R squared UR is equal to some constant C1. And so UR is given by C1 over R squared, right? But again, this is all just a function of one variable, right? This means that the first derivative of U with respect to R is C1 over R squared. I know how to take the antiderivative of both sides, right? So this tells me that my function U of R is the antiderivative of the left-hand side. So this is minus C1 times 1 over R plus C2, right? And that's the solution. So this is a harmonic function. In particular, we know if we want to go back to the original coordinates, right? So in x, y, z coordinates, we get U of x, y, z is equal to minus C1. Remember, R was just the square root of x squared plus y squared plus z squared, and then plus C2. Right, and so this analysis shows that this is a harmonic function. Right, so if you take the Laplacian in x, y, and z of this function, you're going to get 0. It's a very lengthy calculation if you do it this way, which is why it helps to use spherical coordinates instead, because for spherical coordinates, this calculation was relatively simple. If you try to directly check that this is harmonic, it's going to take a while. I mean, you can do it if you have 20 or 30 minutes to spare and check your work, but it could take a bit of time. It may not take 20 minutes, maybe like 10 or 5, depending on how fast you are. But right, and so just as I mentioned with the case in 2 dimensions where we got this log R or log of square root of x squared plus y squared, this particular harmonic function, which is the like rotationally invariant harmonic function, or the radial function which solves this equation in 3 dimensions, this turns out to also be a very important harmonic function, which is very similar to like the source function for the diffusion equation, and now in 3 dimensions rather than in 2 dimensions. Great. Okay, and so that ends the introduction into basic symmetries and properties of Laplace's equation. What we'll do starting with the next lecture is talk about how to solve certain boundary value problems for this equation in detail. And so next time, actually, I mean, we're going to be using Fourier series as we did for the diffusion equation and the wave equation in finite domains. Right, so we're not completely done with Fourier series. They'll still show up from time to time. All right, thanks.